Welcome to today's training. Seismic analysis of earth dams. I've got a lot to cover, so I guess I'll get right into it. I like to start things off with motivation, kind of let everybody know why we're doing this. So give a couple case histories of seismic dam failures in the past. Go into seismology itself. What is it? How does it affect the problem that we're looking at? And then go into geotechnical engineering and a refresher course on that. Finally finish with some closing remarks. So one of the most well-known is the 1971 San Fernando Dam. Magnitude 6.5 or so, accelerations 50% of gravity, and a relatively close fault, manifestations as close to a mile. One thing to point out on this photo is all of the houses and development below the dam. Some of the construction things that are important, this is a hydraulic fill for a majority of it. That's going to come into play when I talk about the failure. Here's a couple schematics of the dam. One important feature here is the rolled earth berm on the front. That was added later, and it could contribute to why the upstream slope did not fail, or the downstream slope and the upstream slope did fail. It was a liquefaction failure in the hydraulic fill material that contributed to this slope moving into the impoundment. Another picture, so like I said, there was a major slide. 80,000 people were evacuated for almost a week. It was only 4 feet from being overtopped. 35 feet of freeboard down to 4 feet of freeboard in one event. So the big question here is a bunch of what ifs. It was below normal pool at the time that this event occurred. What if it was at normal pool? What if the earthquake was a little bit longer and moved just a little bit more material? There's actually an upper dam connected to this one that showed a settlement of its crest. What if that dam had failed and then impounded even more water into this structure? This is another picture, a little crisper, other side. This is once they exhumed it, so this is, and then drained it. This is what it looked like on the upstream slope. So San Fernando is not the only evidence. There is one in Oregon. No, this is Montana, Hebgen Dam. Anyway, crest settled, concrete cracks. There were cracks all over. This one, a big feature was landslides into the impoundment that created a bunch of these waves. There was a fault that was assumed to happen within the impoundment and created a Seiche wave, that S-E-I-C-H-E word that's up there, buried in this plot. I should mention that I will have this available for you guys to look at. I know I'm going through it very fast, and you don't have time to read everything, but this will be available afterwards. Anyway, the landslides caused overtopping of the dam on multiple times, at least 4 in the written history. Massive rock slide actually dammed up the exit of the spillway. So it exited into a river. That river got dammed up and impounded all the way up into the spillway. So you can actually see the spillway on this one. It's cracked, and the water, is that the right picture? Anyway, there it is. That's the picture I'm looking for. You can see the water at the edge of the spillway there. There's also another one, even earlier, 1925, Sheffield Dam. There's another California dam. Hydraulic fill on this one as well. Another liquefaction failure that moved material. And this one actually did flood the downtown, a couple of feet. At the time, it wasn't highly inhabited, so only a couple houses were destroyed. So another interesting fact about all those, they're hydraulic fill. The Lake Murray Dam is partially hydraulic fill as well. Hydraulic fill is a form or a method of placement of material where they make it a fluid and kind of flow it into place, kind of like concrete, and then they let the water dissipate out. So the thing there is that it gets a very loose structure, and you've got a lot of pore spaces, and I'll talk about liquefaction later, but that contributes to this liquefaction susceptibility. So an earthquake is just an energy release in the ground, and that energy is transmitted through the earth by waves. We call those P waves and S waves based on their the way that they transmit the energy. A P wave is sometimes called a compression wave because the movement of the individual particles is in the direction of the movement of the wave. So if the wave was moving towards you, the particles would be moving in and out from me and ramming into each other and pushing the other one. A shear wave is one where the contacts are moving perpendicular to the way of flow. So if you got two particles connected and you slide one on the other, it'll pull the other one with it, and you get this slinky type wave that they call a shear wave because of the mechanism that contributes to the propagation of this wave. When they hit the surface, they do different things. Because there's nowhere for the wave to transmit, some of it gets rebounded, and you get these random features, whether they be circular or different motions within the ground surface. When a large event happens, it will actually ring the entire Earth. The entire Earth will feel these waves multiple times. And during the Cold War, they did a lot of research looking at these waves to try to figure out which ones were nuclear testing and which ones were seismic. So they did a lot of advancement on this back in those days. But the long story here is that the way that these waves transmit and rebound, they tell us something about the structure of the Earth. And part of that structure is that there's a hard crust, and there's a molten or viscous, semi-viscous fluid in the middle that does not allow shear waves to transmit because shear cannot transfer through a fluid. Fluid doesn't have shear strength. There's these different boundaries. The MOHO, I'm not even going to try to pronounce that word, but that is a very distinct difference between wave propagation between those two materials, and it gets a lot of rebounds. It is a very important thing in seismicity on how these waves get transmitted to the surface. Another interesting thing about the molten core is it allows a flow to happen within the Earth. They're kind of convection currents. As the molten cools, it moves up. As it heats, it gets pulled back down, and it creates these currents. When it slides underneath the crust, it will actually move the crust. And you get these spreading ridges, predominantly in oceans. There's one in the Pacific Ocean, there's one in the Atlantic Ocean. The thinnest point of crust is where the magma escapes from the mantle into the crust and it creates new ground. These linear features are just magnetic. It's one of the ways that they figured out that this was happening. I'm not going to go into that. But so when these elements of the crust meet, you've got an oceanic crust that tends to be thinner and denser than the continental crust. And it will slide underneath the continental crust, which creates these avenues for magma to come up. It'll bunch up the continental crust in that region, creating mountains, creating volcanoes. And it's also a large fault feature that produces very large earthquakes. Some of the greatest earthquakes you've heard of, the Chile one, the ones in California, the Japan one, they're all subduction zone earthquakes. So this kind of brings us to this map that they've developed based on this history of crustal movement and earthquakes and volcanoes. And they've created all of these plates, they call them, and the boundaries are based on these different features. So if you look at western United States, that is where the San Andreas Fault is. It's probably the most active one in the United States. So a fault. These crustal movements have to be accommodated somehow. They move on pre-existing discontinuities in the ground. We call these faults. And depending on the shape of that fault, we give them different names. The dip slip is probably the most common, and there's normal and reverse. Normal is if it would slide down that slope. So you notice how this one's sliding down. That would be a normal movement. If it's pushing against each other and rising up, that's counter to what gravity would have, so it's a reverse fault. And if they're moving laterally, it's a strike-slip fault. As you can imagine, these different motions create different wave action, so the source characteristics do come into play when we're looking at the earthquake and the expected motion that we get. So there's a thing called elastic rebound theory, probably the best definition of how these earthquakes occur over and over in the same spots. And that is that these plates are in constant motion. The motion occurs on these boundaries. And these faults can resist that motion in some way based on the strength of that fault. And as they resist that energy, the motion that would have happened turns into a stress on that fault, and that stress is the capacity for energy release. So if it's weak and ductile, it'll release slowly. If it's strong and brittle, it'll release all at once in a very high energy. The really cool thing about this is it was first theory that allowed us to define foreshock and aftershock. So all of these faults are not uniform. There are anomalies. There are strength anomalies. There are geometric anomalies. So some of these will slip a little bit earlier than the rest, and the rest will hold it. That is what they call a foreshock. But you have stronger zones that if the entire thing releases, except for this one section, you're going to spread that stress to that section, and eventually it's going to go, and that is how they define aftershocks. And it also goes into this recurrence interval thought. If the plates are in motion and it's relatively constant, and the strength of this joint is relatively constant, the time it would take to reach the strength of that joint would be the same or similar each time. So the assumption is that these recurrence intervals are going to be relatively consistent throughout the duration of that fault and the movement of the crust. So we have to describe how big these are. One of the first ways to do it was an intensity. It's just a qualitative measure of what was observed, how many things got broke, kind of talks about energy in a way, because it takes a certain amount of energy for these certain features to happen. All of these different people develop different ones, but they're basically a scale from 1 to 10 or 1 to 12. Modified Mercalli's the most important in the US, so I've listed some of these. For instance, number 3, it's felt quite noticeably indoors, especially on upper floors of buildings, but many people do not recognize it as an earthquake. Standing motor cars may rock slightly, but it feels like a passing truck. You get into these more intense ones, like number 7, when it gets very strong, everybody runs outdoors. Damage negligible in buildings of good design, moderate in ordinary structures. Anyway, you guys will have this slide. You can read through it at any time that you want. The problem with intensity is that it's qualitative. There's no measure of things. As an engineer, we like values and magnitudes, and so we created all these different magnitudes. In the beginning, we only had surface measurements, so it was kind of how much energy reached the surface. And the only difference between this and intensity is that we used a measurement, and created an equation and gave it some number. Until we got into the moment magnitude. This was the first and only one that actually calculates the energy at the fault. And it's independent of where you measure it from. You can get all these different surface magnitudes and surface intensities from the same moment magnitude depending on where you're at on the Earth. Yeah, I'll leave it at that. So, little gauge on how much energy there is. That subset there tells the typical range of seismic energies, and you're looking somewhere between the world's largest nuclear explosion and the entire annual use of energy in the US in 1 year. So that's a lot of energy. So even though we know these energy limits and we know that we've got magnitudes, we got to measure it somehow. So they've come up with seismographs. It's a hanging weight with a stylus on it. So when the Earth moves, the mass does not move, and it creates these traces. This trace here was actually during the Virginia earthquake, recorded at Cornell University. It's still on display there now. Interesting feature here is this planar right here. That is the maximum that this instrument can record. So it has reached the limit. So to fix that, they use accelerometers. Accelerometers can measure much higher accelerations. They can put 3 different directions on them, and they're just a lot more robust instrument than the seismograph, although seismographs are still used today. Once we get these signals, there's certain things we want to look at. Of course, you look at peak values, whether it be acceleration, velocity, or displacement. They'll be different depending on the frequency, which is probably the more important part of the earthquake, is this frequency content, because every building and structure has a natural frequency. If the frequency of the earthquake matches the frequency of the building, you get a lot more drastic response in the building. So we have multiple ways of doing that. The Fourier spectra, it's a long algorithm. I'm not going to go into that. But the response spectra is what we use predominantly. So the Fourier is this messy looking one on the right. You can window it. The response spectra is this one here. It's a lot cleaner signal, gives us more intuitive results, and it also more directly related to a structure, because we pass the entire earthquake time history through a single mass with a spring system and measure the response of that mass and spring system, which has a natural frequency. We will change the mass and the spring so that it has a different natural frequency, and we'll do that again, and we'll do that at every natural frequency and create this response spectrum, which is what will it make a structure of this period do. Kind of told not to talk about this too much because it's a little complicated, but it's also one of my favorite slides. So earthquakes are extremely complicated when they get to the surface. Why is that? Because they go through many ways to get to the one spot. The fault will rupture and send this stress wave out, but it's one pulse. It is not like it's going to be vibrating at the source. It just moves and it releases, and all these waves travel through the ground. They go in 360 directions. They go through different interfaces, and when they hit the interface, they partially reflect and partially refract. So one wave will turn into 4 waves, and then each of those 4 waves will hit another interface and turn into 4 more waves. And they all take longer and shorter times to get to the wherever you're measuring it, and they come at different times, different phase shifts, so it's a combination of all these individual rays that hit your site at one time, and it creates this very complicated signal. All right, so you guys are saying, I'm in South Carolina, these are on the West Coast, these are in California, these are in Japan. So that's right, this is our continental plate here. We're not quite in the middle, but you notice these vectors with numbers on it? Units don't really matter, but they're relative motion of that crustal plate, and they're not the same. So 19, 15, 24, 25. So there is some distortion within this plate that is accumulating stress. And on the right, you see that there are two main areas that have released large earthquakes in historical past. New Madrid and Charleston. So we call these interplate and intraplate. Charleston is an intraplate earthquake. So relative movement changes. On the interplate, it's so active that you got this wide distribution of fractures, and the waves have to cross over all of these fractures, and they lose energy a lot quicker. Another thing, because it's so much more active, you have a lot of records on the West Coast. You have examples of time histories from all of these different events. Odds are there is an event recorded on the fault that you're looking at. So you can just pull that time history and be like, oh, this is what it looked like last time. So on the East Coast, we don't have that. Source characteristics is another kind of obvious one, but we have to guess on all of our fault structures over here. We call it paleoseismology, and we call it science, not guessing. But it is still a lot of guessing and a lot of inferences to make. This here is a list of every recorded earthquake as of January with a time history record. You notice there's a few in Charleston, but the highest one is 4.7. This magnitude scale is exponential, so a magnitude 7 is like 10,000 times larger than this event right here. So even though we have a recorded history of it, it doesn't tell us much. Here's a list of all the important ones. You'll notice that some of those are intensities because they were before recorded history. Others have magnitudes. Those were typically after recorded history. Intensity maps. One thing here to notice is these features right here that have isolated higher pockets of intensity. Those are local side effects that I'll get into in a bit here. There's another earthquake, the Union County earthquake. It was the next largest one that happened in South Carolina. This was in the Piedmont, the upstate, so slightly different fault regime in that area. So I was talking about inferring faults and this scientific guesswork. They're pretty good at it, and they've done a lot of math, and they have determined that these are where the most likely locations are of the faults beneath the coastal plain. On the northwest side, you see that these are all mapped because it's rock. These can be exposed at the surface. Beneath sand, there's no manifestation at the surface, so you have to do other methods. So, return interval is a pretty important portion of the problem that we look at. How often is this going to occur? Is it going to be within the lifespan of our structure? So there are recurrence laws, which if we were in a highly seismic area like California, those would be very beneficial to us. We are not. So we have to do what's called paleoseismology. One of the things is looking at features that occur during earthquakes that take a high energy or certain amount of energy to do, so we can look at those. Liquefaction is one where the sand loses strength because of pore pressure buildup. I will get into that later as well. But as that water tries to escape, it pulls sand with it as well, and it creates these sand boils and these sand seams. You've also got slope failures that you can back calculate the energy required to do that slope failure. Tombstones in Japan have been used very widely because they're different sizes, different dimensions. They take different amounts of energy to topple over, and they also have different natural frequencies. So you can go to a graveyard and be like, oh, only this size tombstone fell over. That means the predominant period of my earthquake was this. So based on all this information, the Charleston earthquake has a return interval somewhere of 500 years, plus or minus 300 years. So that's a tight little window. I'm sure you guys can do the math on that one. But there's at least 2 historic events that have occurred. Those are both AD. I forgot to add that. I should have added that little detail. All right, that's enough seismology. I know you guys are starting to gloss over. But the point of that is to show you that, yes, we do have a concern for seismic activity in South Carolina. So we should be considering it in some of our designs. And how do we do so? So first off, we have to determine what earthquake is going to hit us, what our design parameters are. So our entire goal is to design our structure to resist it. But we need to know what we're trying to resist before we can design a resistance. We do what's called seismic hazard analyses. It's a quantitative approach to evaluate the energy that reaches our site. It's a 4-step thing. You got to identify your source or sources. You got to select an analysis method, deterministic and probabilistic. You got to perform the analysis, and then you got to apply these local site effects. And then you have your parameters used to design your structure. So the source identification, there are several ways to do this. I kind of talked about paleoseismology. If you see these features, odds are something has happened in the past. You can look at outcrops. If you see these fractured surfaces, or you see these 2 materials that are offset, odds are there was some sort of faulting occurred in that area. On a grander scale, the San Andreas Fault with aerial photos, should have added a scale, but that's a great distance right there. Here's just another picture of a sand dike. This is a liquefaction feature. Other ways is tectonic evidence. You map the movement of the plate. We know that there's stress accumulating because there's differential motion. I talked about historical seismicity. In some countries, that's quite a long time. In the US, it is not. And then, of course, there's instruments. If you have them set up and they recorded an earthquake, you probably have earthquakes. So, deterministic and probabilistic methods, I'm going to try to go through these really quickly because they're pretty dense. But you identify your sources, whether they be linear or aerial features. You go to step 2, you select a distance, usually the closest distance. It can be epicentral or hypocentral. Epicentral is distance along the surface. Hypocentral is a tangential distance, so the actual distance from your site through the earth to the fault. You have to select a controlling event. So of all of these, which one's going to give us the highest result? And then you formalize your hazard and give it values. This works great because it ends up with a particular site. In the southeast, like Charleston, that is the dominant event. No other event is going to contribute to your hazard, so that is a very good method to do it. If we're in the upstate, however, though, you saw that Union Fault that's a lot closer, and it could contribute to this. So then you have to go to a probabilistic one. Oh, I forgot about this slide. Sorry about that. Anyway, just goes over some benefits of the deterministic versus the limitations. And the probabilistic So when you have more than one site that could contribute to this, you have to look at probabilities. And probabilities, you know where this thing is at. Probabilities that your time estimate on these are correct. Probabilities that your ground motion is going to be the same that you expect. And in the end, you end up with an uncertainty combination throughout every single aspect, and you get the likelihood of a particular event occurring at a particular location, and it's just a lot more robust if you're dealing with a lot more potential sites. All right, back to wave propagation. This will go into our local site effects, which tends to be a big concern, especially on the Charleston area where there's so much sand and soil for the wave to pass through. Anyway, as I've said, the fault ruptures, the wave travels through the earth, it reaches geologic boundaries, it's reflected and it's refracted. And since, I guess this third bullet doesn't make sense to you guys, but shear wave velocity decreases as you move towards the surface, and if you reach an interface of two materials where the top has a lower speed, it curves upward. And this happens over and over throughout the entire crust as it gets slower wave speeds towards the surface, and this wave ends up coming in nearly vertical when you reach the site. This works to our benefit. But some basic definitions, is a free surface, the bedrock motion, and the outcropping motion. The bedrock and the outcrop are the same thing, they're just recorded at two different locations. The outcrop is on the surface on the bedrock, and the bedrock is underneath some sort of sand layer. These are considered to be exactly the same. And the free surface motion, if it goes through soil, is not the same as the two bedrock. Natural frequency. So I kind of mentioned that every structure has a natural frequency. Is how I figure that is you've got a wave that's moving up and then it gets rebounded back down. If the speed and dimensions of this layer are such that the upward and downward waves are in phase, you double your amplitude motion because these two waves combine. If they're out of phase, you get a deconstructive combination and it makes it smaller. So you get these amplifications. That's what we call a natural frequency, is when it's basically the speed of that layer and the dimensions. Resonance, this is something that occurs when your wave going up is in phase with the returning wave. We call that a resonance. It's the same feature. Impedance contrast is the difference in the wave speeds of the two materials. One goes much faster than the other, then you're going to get a more refracted than reflected, and vice versa, and this will contribute to the wave propagation. So the important thing about this goes back to that response spectrum discussion. We've got period on the bottom. Period is the wavelength of a wave coming in. So a longer period means that wave would take longer to make a full cycle. A shorter period means that it takes less time to make a complete cycle. If you end up going through soft soils, you get a softening of the material, and you get this lobe here, where you get a lot of energy at like a 1 second period. A lot of longer structures, like dams, would have a 1 second period, or in the range of 1 to 5 second period. So when you get energies that correspond with that, it's much more problematic for the dam. If you're on rock, it concentrates more on these high frequency, low period events. So we have to transmit and change this wave from the source to the surface in some way. We do this with what we call soil response analyses. There's one-dimensional, two-dimensional, three-dimensional. 1D is the simplest. It's an equation that will create this transfer function, and I'm not going to go into the minutia of it, but it changes in the frequency domain, and then you get a new time signal. You see that this resulting is more spread out. These are a lot tighter waves than these are. So this has a longer period contribution. This is just another example of the same thing. So it's a shorter duration, about 20 seconds. This one spreads out to about 40 seconds. These are the same event, just different locations based on the one-dimensional transfer function. So there's also these other aspects. Not only is it one-dimensional, two-dimensional, there's linear versus equivalent linear versus nonlinear. And soil is a nonlinear material. Let me see if I can... So here we have strain and stress. So you guys are not engineers. This here is displacement, and this is force. But they're normalized to a specific area. Generally, when you move an object, it will start to accumulate stress. So as you displace it, it'll get a force on it until it reaches some peak value. In some instances, it'll actually lose strength once it reaches its peak and level off. That's a residual strength. But this is a nonlinear response. We are looking at the shear modulus, which is the slope of this line here, which is not always the same. The initial one is really steep, but say you're out here, it's less steep, so it will change throughout the period of this. And that's why 1D linear is not very effective. They developed a way to get around that. It's an equivalent linear, and that's where you have to match the strain and the shear modulus that you use. So you'll pick a shear modulus, run through the analysis, figure out what strain it gave you, see if that's compatible with what you selected. If not, you do it again with a new shear modulus until the shear modulus you selected is compatible with the strain that it gives you. Unfortunately, this is not always accurate as well because every single cycle, these parameters change. So that's when you'd go into a full nonlinear analysis where you update all of these values in every time step, and you solve a small section and then time step it forward from that point. So these are very powerful, but they're also very sophisticated. It's one of those you want to build up to. You don't want to jump straight into a nonlinear model because there's a lot of parameters you need to know. Kind of talked about 1D. This is hardly ever allowed. It's almost always 2D because we're looking at some feature. If it's long enough feature, we can assume that the boundaries don't impact the section that we're looking at. And then we can use a 2D analysis. If, however, you've got a very short structure or non-linear soil distribution or different size structures that are contributing to this, you need to do a full 3D analysis. Again, just like linear, equivalent, and nonlinear, you want to start with the simpler and use only as sophisticated as you need to. So these side effects, I keep talking about California and South Carolina. It's because California is where all of the earthquake studies come from, and we're in South Carolina. And the rock here is so much harder, it is hard to explain. But when the Charleston event happened, when the New Madrid event happened, they were recorded in Canada. Waves in California don't travel that far. So it's a really big deal that we have these solid, competent rock in this area. And we've also got a coastal wedge. So we've got up to 2,000 feet of soil in Charleston that this wave has to propagate through. And that's a lot of mechanisms that can change this wave and change the content of that wave. You've also got geometric effects. This is just the rebounding of the wave, as I was talking about, reflections and refractions. If it comes at an angle, say it's on this peak here, it's going to kind of bounce up here, and they're all going to accumulate at that peak. So you get higher accelerations up here than you would in the trough, because the opposite happens there. It spreads away from that instead of focusing. Basins is another one. This is actually an example from Honduras. Did some reconnaissance down there. It was a pretty cool trip. This building is a judicial building. The building on the bottom is a stadium. Same construction, same height, same everything. They're maybe a half a mile apart, but there's so much damage on the judicial building, and it turns out there was a company that had developed that land over a marsh. They filled it in, flattened it off, and then they abandoned the site for a better construction site. And the government decided, oh, look at this nice flat plot here. I'm going to pick that up, and they built their judicial building on it. And this is just an example of basin effects, because that swamp that was filled in with soil trapped these waves, and it bounced all over, and it created a more complicated wave when it hit that structure. It amplified certain parts that caused this building to deteriorate. Some other ones are disruptions. So these are actual faults that are manifested on the ground. This would be something in the upstate that might be a big concern, because these faults can actually manifest on the ground. You get potential loss of freeboard if this were to occur within the dam or even right next to the dam. Like, imagine if that bridge section that was collapsed was where your dam was, and this was within the reservoir. You might lose all your freeboard just because of the movement of that rock. Of course, there's inertial loading, so the earthquake itself has energy that is going to excite the dam. Liquefaction. Talked about liquefaction a lot. So I might as well go into the mechanics of liquefaction, I guess. It happens in water-filled soils. When a sand in particular is vibrated, it wants to roll into a tighter configuration. So it wants to fill up the voids. If those voids are full of water, they press up against the water. If the water does not have time to escape, it builds up a pressure and pushes back on the soil. Not necessarily a bad thing, except for sand works on friction, which is a function of how much pressure it has on each particle. So if the water is pushing these apart from each other, they're getting less strength because they have less friction. And until that water pressure dissipates, you are going to have a very low strength material. But it causes sand boils, it causes tanks to sink and rise. It'll take over buildings that was at once like all grass. This is all from Honduras, by the way. And lateral spreading. So if you have a liquefied section with a competent solid material on top, that material will tend to slide on top of the liquefied material, and it create these huge fissures. You've got the Himoyan River. I can't even pronounce it. It's a Spanish term. But major agricultural region, this levee had lateral spreading along the entire 200-mile length of it. It was a very phenomenal failure. Just more pictures of the same thing. I did not show how long that stick was that he's sticking down there, but that stick is 7 feet tall. It was taller than him when he pulled that stick back out. Seychelles. I kind of mentioned this earlier. That is a large wave that occurs within a closed body. It is basically a tsunami that is in a lake. I'm sure everybody's familiar with the tsunami ever since the Tohoku, Japan earthquake. Tohoku? Anyway, doesn't matter. These events can overtop dams. They can come from many sides. They can come from that fault occurring within the impoundment. They can come from rock slides filling in the pond and creating a huge wave. But they can do devastating effects to structures of any kind. All right, finally, some actual design portion. All of this is what is an earthquake? What can it do? So if you look at the DHEC manual, it's got a sentence that says you must address it. But it leaves it open to a lot of flexibility. But it also recommends these other 3 documentations, Department of Agriculture, U.S. Army Corps, and Department of Reclamation. So what do they have to say about it? If you look at the NRCS, it's about the same thing. It's just a statement saying that you should address this. It is a concern. You look at the Army Corps, they go a little further. They kind of define some things of interest. So some interesting things are what they define as maximum credible, maximum design, operating basis. These are just different levels of a design earthquake that you would want to achieve. So for instance, the operating basis is one that you would maintain operation even if that event occurred. Another suggestion here is that you've got seismic hazard levels and it is mapped throughout the entire US. We are in the moderate to high in South Carolina. Probably the best one, in my opinion, was the Bureau of Reclamation. They're very thorough. It's a very good document. If you're interested in the seismic regulations on dams, this is the manual that I would go look at. It has a lot of important inclusions. I'm not going to read this whole list, but it discusses all of these and it goes through the analyses. It has different methods that it suggests. Very good document on analysis of dams. So we have to know what the soil is in order to design against anything. So we have to do site investigations. I know this is not hugely related to you guys, so I'll go through it relatively quick. But we start off with a desktop study. You look at reports, you look at aerial photographs, you look at Google Maps. There's Street View, which does a lot of interesting things nowadays. You can learn a lot from a desktop, especially in contemporary times. Surface investigations. You go to the site. You can do surveys. You can do geologic mapping, geophysics, ground penetrating radars. There's a lot of different techniques that you can use in the field without even digging a hole or doing anything invasive. One of these surface techniques is a seismic refraction, where you put all these geophones, detectors, on the surface, and you usually put like a metal rod and hammer it. And then you measure the response, and you can get these distributions of waves. So the idea here is that this wave that comes here, it's going faster on the bottom than this one is right here. And eventually, it's going to come sooner to this location because it's traveling faster. Even though it goes farther, faster, farther, at some point, it will come there sooner, and you can get the distribution of layers this way. There's surface wave spectral analyses. This is one where you do different wavelengths, and depending on the wavelength, you penetrate different depths into the soil. Assuming that it's faster down lower, you can determine wave speeds based on an analysis of these waves. Once you start looking at actually invasively checking this, there's test pits. There's boreholes. You can, standard penetration is probably the most used. I think they've talked about this in previous training sessions, so I'm not going to get into what an SPT is. Becker penetration, if you're in gravel, it will prevent the SPT from working, so you use a Becker. Borehole geophysics and instrumentation. This is kind of like the wave analyses they do on the surface, except for they put the detectors and the transmitters in the hole to measure a specific layer. Cone penetrometers, and these are really sophisticated. They can have geophones on them, so you can do a downhole seismic with a CPT, and you can measure water pressures and field vein shears. One of the reasons the SPT is so popular is because you can collect a sample. This picture up here is a split spoon used in the SPT, and then you can take that to the lab and get what materials in there. You can get different correlations based on that. Or you can do a Shelby tube down here. This is what we call an undisturbed, because it's a really thin tube and it doesn't disturb the soil as much. There's at least some zone in the middle, once you trim it, that is not influenced by pressing this rod into the ground. All right, back to liquefaction. Now that I've described what it is, here's some effects of liquefaction. It's kind of a big deal. It swallows cars, it swallows tanks, pipes will float and break, buildings will collapse. But really the big thing is a loss of strength. And not complete loss, but you're down to 10 to 15% of what you originally had before the liquefaction occurs. And lateral spreading, I kind of talked about that. It creates this slick and slide layer that allows stuff to move on top of it. If you have lateral spreading on a pile, all that soil that is not liquefied will be pulling on that pile, and you'll actually shear it in two. Anyway, so once you have all of these soil tests, in situ tests, your lab results, you have to develop a soil profile. It's a fictitious image of what's in there. It's always complicated, and we try to make it as simple as we can without missing anything. So there's actually a very big art to developing the soil profile, and we spend a lot of time developing that. Selecting reasonable strength is also another very difficult, tricky geotechnical aspect, but also a very important part of that generalized soil profile, especially when you're looking at earthquakes. There's a lot more parameters that we have to define than a typical slope stability. So once we have the profile, You got to determine if it will liquefy, and if not, how do we have to mitigate this liquefaction, because that's going to contribute to the strength of these soil layers that you select when you run your model. So for the analysis, we determine a cyclic stress, whether it be a cyclic stress resistance, which we call a resistance ratio, so it doesn't have the same acronym, or a cyclic stress ratio that is inputted by the earthquake, and then we compare the two of those to determine the factor of safety or the likelihood that this is going to lose energy. This is probably the more important part. I think Jintao talked about this last month on slope stability and all of these different method of slices and things like that. So we do the same thing in seismic analyses, except for we add a horizontal acceleration component, which is what I'm calling the pseudostatic method. And basically, instead of having just gravity pushing down on this and then the angle of the bottom creating the driving force, you've actually got an acceleration at the centroid of each slice pushing it to the side, and you evaluate equilibrium based on that horizontal pressure and the gravitational pressures. And if that is not enough, you move into a more robust finite element, finite difference. This one, you've got all these different nodes, and you balance functions throughout the entire mass model. And the idea there is that each node is related to another node, so you have to balance the difference between the two results until they all are uniform and matched. So once you do your stability analyses, you determine whether or not you need a deformation analysis. If your factor of safety is high enough, you assume it's not going to fail and you don't have to do this. But if you have a marginal factor of safety, you have to estimate some sort of deformation. We do this in a few different ways. Newmark, back in the 1960s, developed the most used one. It is basically assuming you've got a yield acceleration, which is when your factor of safety equals 1. That is consider your yield acceleration within the pseudostatic method. And that is input right here. So anytime that you go above that, you begin to start accumulating velocity. And you'll continue to accumulate velocity until the acceleration drops below the yield, and then you'll slow down. But you get this stepwise displacement where it moves, moves, moves. And you can actually estimate the amount of this movement by running your time history through a Newmark analysis with a specific yield acceleration that can also change with time if you make it more complicated. And there's also finite element, finite difference. So, yeah, remediation techniques. I'm getting pretty close, guys. Well, so there's two main ways to do that. There's structural or there's foundation improvement. Structural, we saw on the the first dam that I showed you guys. It had an extra berm that helped prevent the downstream side from failing. That would have been a structural modification. You can modify appurtenances, all sorts of things. For the foundation improvement, it's typically either densifying it or putting something in it to make it more dense. Here's just an image of another berm, a couple different options there. Excavation and replacement. Always an option, not always the cheapest option. Deep dynamic compaction. This one is typically done before a dam is built. It's hard to drop a huge weight on a dam and improve its condition. But on this one, you create a grid and you drop this hammer over and over, and it compacts all the soil beneath it in the grid. You've got vibro-compaction, vibro-replacement. This is how stone columns are built. You stick a vibrating mandrel into the ground and then pour in sand and gravel as you retract it and fill in that area. This is twofold. It'll densify the material around it, and it will also add a strong stone column within grids on your site. Wick drains or earthquake drains, very similar, different shape. The earthquake drain is circular, so it's got a larger volume. That's so that when your liquefaction occurs and it's trying to exit or purge all this water, it's got a volume that water can go into. If your tube is not large enough, you can create a gravel layer on top of it that'll act as like a ballast or an overflow for that wick drain. Some of the other ones, you actually go in there, you do deep soil mixing, you can do jet grouting, you can do all this stuff. I was actually talking with Steve Whiteside the other day. He was telling me about a project that he worked on where they implemented this exact solution. So. All right, closing remarks. Just talk about what to look at when you're doing permit applications. Kind of just went through the regulations and saw what the regulations dictated you do, and figure we could have more of a discussion on this than me tell you what you need to look for. You guys have probably seen more permit applications than I have, so. That being said, any questions, comments?